Good morning, everyone, and welcome to today's presentation. I'm Dr. S.K. Singh, and I hold a PhD in this field. Today, we'll be exploring the basic theory of column chromatography. We'll start with the fundamentals, understand how it works, and discuss its applications. I'm excited to guide you through this topic and look forward to a productive session. Let's get started. Let's go through some key terms and their definitions that are fundamental to understanding chromatography. First, the mobile phase or carrier is the solvent that moves through the column, carrying the mixture with it. Think of it as the vehicle that transports everything along the process. Next, we have the stationary phase or adsorbent, which is the substance that stays fixed inside the column. This is crucial because it interacts with the analytes, helping to separate them based on their different affinities. The eluent is simply the fluid that enters the column at the start of the process. It's typically the same as the mobile phase, carrying the mixture into the system. As the process continues, the fluid exiting the column is called the eluate, and this is what we collect in flasks for analysis. Elution, then, is the process of washing out a specific compound through the column using a suitable solvent. It's a controlled way of separating out the components based on their interaction with the stationary phase. Finally, the analyte is the mixture we want to separate and analyze. It consists of multiple components, each with different properties that allow us to distinguish and identify them during the process. Connecting all these concepts, understanding the roles of the mobile phase, stationary phase, eluate, and analytes helps us grasp how chromatography effectively separates complex mixtures. Let's take a closer look at ion exchange chromatography. This technique, also known as ion chromatography, is a powerful method for separating ions and polar molecules. The key idea here is that separation is based on the molecule's affinity for the ion exchanger. The stationary phase in this process is an ion exchange resin, which carries charged functional groups. These groups interact with oppositely charged groups on the compounds we want to analyze, effectively retaining them on the resin. This method is incredibly versatile because it works with almost any charged molecule, whether we're talking about large proteins, small nucleotides, or amino acids. The resin itself is a solid phase, and what's interesting is that it's covalently bonded with either anions or cations. When the sample, or solute, is introduced in the mobile liquid phase, ions of the opposite charge are attracted to the resin through electrostatic forces. The beauty of ion exchange chromatography lies in how it separates analytes, based on their charges. Molecules with different charge intensities or types will interact differently with the resin, allowing us to separate complex mixtures efficiently. This technique is fundamental in many analytical applications, especially when precise separation based on charge is required. Let's continue with our discussion on ion exchange chromatography. As we've seen, this technique is a powerful method for separating and purifying ions and charged molecules. It relies on the principle of oppositely charged ions attracting each other, which allows us to selectively bind target molecules to a resin or resin bed. In this slide, we're focusing on some key points. First, the process involves passing a mixture through a column packed with an ion exchange resin. The ions or molecules we want to isolate will bind to the resin based on their charge and affinity. Then, by changing the pH or ionic strength of the elution buffer, we can selectively displace these bound molecules and collect them separately. It's important to highlight that the choice of resin, whether cation or anion exchange, depends on the charge of the target molecules. This specificity is what makes ion exchange chromatography so versatile and widely used in biochemistry and molecular biology. Finally, connecting to the overall theme, understanding these principles helps us appreciate how ion exchange chromatography fits into the broader context of protein purification and analytical techniques. It's a technique that combines selectivity, efficiency, and scalability, making it indispensable in research and industry alike. Now let's continue exploring ion exchange chromatography. As we discussed earlier, this technique is all about using charged resins to separate ions and charged molecules based on their affinity for the resin. On this slide, we see that the process is often extended or refined, which is why we refer to it as const or continued. The key idea here is that ion exchange chromatography can be tailored to separate a wide range of ions, from small inorganic ions to larger biomolecules, by choosing the appropriate resin. The separation depends heavily on the charge properties of the molecules we're interested in, which makes this method incredibly versatile. It's also important to note that the process involves passing a mixture through a column packed with a resin, where ions are exchanged based on their charge interactions. This exchange can be influenced by factors like pH and salt concentration in the buffer, which we can manipulate to improve separation efficiency. Connecting this to our overall theme, ion exchange chromatography is fundamental in biochemistry and molecular biology, because it allows us to purify proteins, nucleic acids, and other biomolecules with high specificity. Understanding these key points helps us appreciate how this technique fits into the broader context of analytical and preparative methods. Let's dive into how the mechanism of ion exchange works. To effectively bind charged molecules, the mobile phase typically has a low to medium conductivity, which means it contains a relatively low to medium salt concentration. This environment helps promote ionic interactions without overwhelming them. The key driver here is ionic interaction itself. The molecules in the sample bind to the solid support through these electrostatic forces. Specifically, the charged groups on the molecules interact with functional groups on the resin or support material. Think of it as a kind of molecular handshake based on opposite charges. Now, the strength of this interaction depends on how many charges are present and their positions on the molecule, as well as on the functional groups on the support. More charges or certain arrangements can make the binding much stronger. When we increase the salt concentration, usually by applying a linear salt gradient, we begin to weaken these ionic interactions. Molecules with weaker interactions will start to come off the column first, as the salt essentially competes with the molecules for binding sites. On the other hand, molecules that bind more strongly, those with more or better positioned charges, require a higher salt concentration to be eluted. So, as the gradient increases, these stronger binders come off later. It's also important to note that ion exchange resins generally have a high binding capacity. This is especially critical in process-scale chromatography, where handling large amounts of material is necessary. For analytical scale separations, however, this capacity is usually more than enough and not as critical. Overall, this mechanism allows us to selectively elute molecules based on their ionic properties, giving us a powerful tool for purification and analysis. Let's talk about buffer pH and why it matters in chromatography. As a general rule, the pH of the mobile phase buffer should be set between the pI or pKa of the charged molecule and the pKa of the charged group on the solid support. This range ensures that the molecule and the support interact optimally. For example, in cation exchange chromatography, if the solid support has a functional group with a pKa of 1.2 and your sample molecule has a pI of 8.2, you would typically run the system at a pH around 6. This pH balances the charge states for effective separation. Similarly, in anion exchange chromatography, if the molecule has a pI of 6.8 and the solid support has a pKa of 10.3, you might choose a buffer at pH 8. This allows the molecule to carry the appropriate charge for separation. Now, let's look at how changing pH can be used intentionally to influence separation. Adjusting the pH of the mobile phase can alter the charge on the molecules. For instance, in cation exchange chromatography, increasing the pH causes the molecules to become less protonated and less positively charged. As a result, these molecules can no longer form ionic interactions with the negatively charged solid support, leading to their elution from the column. Conversely, in anion exchange chromatography, lowering the pH makes molecules more protonated and positively charged. This increase in positive charge weakens their ionic interaction with the positively charged support, causing them to elute as well. These pH adjustments are powerful tools to fine-tune your separation process and improve resolution. Now, let's talk about salt gradients in chromatography. In most types, except for size exclusion chromatography, we start by injecting our protein sample onto the column under conditions where it will be strongly retained. This means the proteins are held in place initially. Next, we gradually increase the salt concentration, usually in a linear fashion, to elute the different components. Think of it as slowly turning up the volume until each protein comes off the column at its specific salt level. Alternatively, instead of a smooth gradient, we can use a step gradient, which involves sudden jumps in salt concentration. This method requires simpler equipment and can be quite effective, especially if we already know the salt concentrations that elute our target proteins, often determined through initial linear gradient experiments. Now let's consider a specific procedure involving a mixture of arginine and aspartic acid passing through a cation exchange column. Here, arginine, which has an extra positive charge, sticks to the negatively charged resin. Aspartic acid, bearing a negative charge, doesn't adhere and comes out first. When we introduce a weak NaOH solution, it neutralizes the positive charge of arginine, weakening its affinity for the column. Then, sodium ions, Na+, displace the arginine, allowing it to finally elute. This process highlights how adjusting salt concentration and pH can be used strategically to separate and purify different proteins or amino acids based on their charge properties. It's a fundamental concept that ties back to our overall understanding of chromatography techniques. Now, let's take a closer look at the different types of ion exchange resins. First, we have the cation exchange resins. These are typically made from materials like polystyrene sulfonate resins, CM Siphacos gel, or CM cellulose. What makes them special is that they bear acidic groups, which allow them to immobilize cations from the surrounding solutions. Essentially, they attract and hold onto positively charged ions, which is crucial in many separation processes. On the other hand, we have anion exchange resins. Examples include DEAE cellulose, trimethyl-aminopolystyrene, and DEAE Siphacos. These resins contain basic groups that ionize into fixed positions, creating negatively charged sites. These sites then immobilize anions from neighboring solutions. So, in summary, cation resins target positively charged ions, while anion resins are designed to capture negatively charged ions. Recognizing these differences helps us understand how each resin type plays a vital role in various separation and purification applications, fitting into the broader theme of ion exchange chromatography. For further support, please feel free to reach out to us through the contact information provided. We're here to help with any questions or additional assistance you might need. Thank you so much for your time and attention today. We truly appreciate your interest and engagement. Remember, your success is our goal, and we're happy to support you along the way. Thanks again, and have a great day.